presenting our work on tempered sigmoid activations for deep learning with differential privacy. This is joint work with Abradeep Thakurta, Shuang Song, Steve Chen, and Olvar Erningsson. So why should we care about privacy? Well, we all know that machine learning is being usefully applied to the analysis of sensitive data sets. This includes data that we find in healthcare, but also when building language models over private correspondence. And we also know from the research community that attacks have demonstrated leakage of secrets. A first example is membership inference. An adversary able to observe a model's predictions can infer whether a particular piece of training data was included to train a model or not. In another example, if we insert very unusual sequences of text in a language model's training set, then we can feed the resulting model with the beginning of the sequence and recover the rest of the sequence. So to counter this, researchers have been working on building machine learning techniques that come with strong, rigorous guarantees of privacy. And these guarantees are typically expressed in the framework of differential privacy, which has become the gold standard in the privacy community. An algorithm is said to be differentially private if it always produces effectively the same output in a mathematically precise sense when applied to two input datasets that differ by only one record. In the example that I give here, the dataset that is at the top of the screen contains the record that corresponds to one individual in particular, whereas the dataset that is at the bottom of the screen is identical to the exception that it does not contain that very record that corresponds to that particular individual. So we want the learning algorithm M to train models from these two datasets in a way that the outputs of the training algorithm are indistinguishable to an adversary. What this means more formally is that we want the probability that the training algorithm M outputting a solution S on the dataset D, which would be the top dataset, this probability has to be very close from the probability that the same training algorithm, this time taking as its input the second dataset D prime, outputting the same output S. And so these probabilities are going to be very close within an interval that is bounded by a parameter known as epsilon. If we can prove that this inequality holds for any pair of datasets D and D prime that differ by one record only, then we have differential privacy. And the smaller the value of epsilon we can prove, the stronger this privacy guarantee will be. Let's now take a look at how we can train with differential privacy. So typically when we train a model, we'll use something like a variant of stochastic gradient descent, especially if we were trying to train things like deep neural networks. Martin Abadi and his collaborators introduced a differentially private variant of stochastic gradient descent as a method for training deep neural networks with differential privacy guarantees. The idea is to, instead of computing average loss values over the entire batch of examples, to start by computing per example loss values for each of the training examples contained in a batch. What this allows us to do is to bound the sensitivity of the learning process to each individual training example by computing per example gradients with respect to this loss for the n model parameters, and then clipping each of these per example gradients to a maximum fixed L2 norm C. Once we've done this, we can then average these per example gradients and add Gaussian noise whose standard deviation sigma is proportional to the sensitivity. This results in a procedure that is differentially private. However, empirically, the test accuracy of differentially private machine learning is typically consistently lower than that of non-private learning. Sometimes this loss may be inevitable. For example, some tasks involve distributions with heavy tails, and the noise that is added by differentially private stochastic gradient descent hinders the visibility of examples contained in these tails. Here I'm giving an example with the MNIST dataset, where we can clearly see that some of the training examples contained in the tail of this distribution are much more unusual than the vast majority of these training examples. This, however, does not explain the accuracy loss of differentially private machine learning on benchmarks that are known to be relatively simple when learning without privacy. Here I'm giving the example of MNIST, where there are very few outliers in the tail of the distribution, but we could also give the examples of fashion MNIST or CFAR10. An important step in providing differential privacy guarantees for an algorithm is to assess its sensitivity. So learning algorithms' sensitivity characterizes how much an individual training point can, in the worst case, affect the learning algorithm's outputs. This is what I illustrated in my slide on differential privacy by looking at the difference between the outputs of the learning algorithm on the dataset that contained the individual's record with the outputs of the algorithm on the dataset that did not contain the individual's records. In general, the ability to more strictly bound sensitivity leads to stronger privacy guarantees. In the paper that I'm presenting today, we were the first to observe that DP-SGD leads to exploding model activations as a deep neural network's training progresses. This makes it difficult to control the training algorithm's sensitivity at a minimal impact on its correctness, so the model's performance in the end. Indeed, exploding activations will cause the unclipped gradient magnitudes to also increase, which in turn will induce an information loss once the clipping operation is applied to bound the gradient magnitudes and control the learning algorithm's sensitivity. Here I'm illustrating this phenomenon on a network trained with MNIST data, where we can see that the blue curve represents the magnitude of the activations on the first layer of the neural network before we switched to private learning. So this is a model trained with normal stochastic gradient descent. And when we switch to DP-SGD to have a privacy-preserving learning procedure, we can see that the activations increase 2 to 3 times in magnitude for that same layer in the architecture. Based on this intuition, we propose to replace the unbounded activations that are typically used in deep neural networks with a general family of bounded activations called the tempered sigmoids. The tempered sigmoids are a family of functions that take the form of the equation to the left of this slide. And here I've highlighted in particular the 3 parameters that allow us to explore this family of functions. S controls the scale of the activation, T is the inverse temperature, and O is the offset. To the right, you can see 4 example triplet values for these parameters and the corresponding function shape. Because this family of tempered sigmoids can in limit represent an approximation of ReLUs on the subset of their domain that is exercised in training, we expect that our approach will perform no worse than current architectures. These architectures use ReLUs as the de facto choice of activation functions. One of the main issues in practice with differentially private stochastic gradient descent is tuning the value of the clipping parameter. If C, the clip norm, is set too low, then clipping introduces bias by changing the underlying objective optimized during learning. Instead, if the clipping parameter C is set too high, clipping increases the variance by forcing DP-SGD to add too much noise. Indeed, recall that DP-SGD adds Gaussian noise to the average of clipped, per example, gradients. This noise is scaled to the clipping norm. This means that large clipping norms lead to noise with large variance being added to the average gradient before it is applied to update model parameters. It turns out that with tempered sigmoids, we can use the 3 parameters, the scale, temperature, and offset, to control the norm of the gradient of the loss function. And with appropriate choices, we can avoid some of these issues that I just described with clipping. In this figure, I plotted the test accuracy of a bunch of models trained with tempered sigmoids as a function of these 3 parameters, the scale, the inverse temperature, and the offset. You can see results plotted on MNIST on the left, fashion MNIST in the middle, and CFAR10 to the right. All of these models were trained with differentially private stochastic gradient descent, and the color of each dot, which corresponds to 1 training run, indicates the accuracy, the test accuracy that the model achieved. If we compare these models with the same architecture trained also with differentially private stochastic gradient descent, but this time with ReLU activation functions, it is very clear that tempered sigmoids significantly outperform models that were trained with ReLU on these 3 datasets. On MNIST, the best tempered sigmoid model achieves 98.1 test accuracy, whereas the baseline ReLU model trained with identical privacy guarantees achieved only 96.6% accuracy. On fashion MNIST, we achieved a best performing model of 86% with tempered sigmoids in comparison with 81.9% with ReLUs. and on CFAR10, we achieve 66% test accuracy with tempered sigmoids compared to 61.6% accuracy with ReLUs. If you take a closer look at this figure, it appears clearly that there is a subset of the tempered sigmoids that perform best when learning with privacy. And these form a cluster of points which result in models with higher test accuracy. So that means points that are closer to being dark green. If we look at MNIST and fashion MNIST in particular, the average value of the 10% best performing triplets is very close to a scale of 2, an inverse temperature of 2, and an offset of 1. And while these observations may not hold for other datasets, it's very interesting to note how these values happen to be very close from the triplet setting, which corresponds to a 10H. For this reason, we explored the particular case of 10H in our next experiment, and our goal was to understand whether it is able to sustain the significant improvement of tempered sigmoids over ReLUs for the 3 datasets that we considered. To ensure that the comparison between ReLUs and tempered sigmoids was fair, we made sure to conduct a thorough hyperparameter search for both the models trained with ReLUs and the models trained with tempered sigmoids. Indeed, an optimizer or learning rate that yields good results without privacy may not perform well with privacy. Among the hyperparameters that we fine-tuned, we found that it is particularly important to set the value of the learning rate to maximize performance given a fixed privacy budget. And this is because the privacy budget limits the number of steps that we can possibly take to update our model parameters on our training set. The table on this slide summarizes the results after we perform this hyperparameter search for each of the 3 datasets. We compare 3 models: the best performing model in the non-private setting, the best performing model with DP-SGD and ReLU activations, and the best performing model with DP-SGD and 10H, which is the particular case of tempered sigmoids that we decided to explore here. Even in their own individually best setting, tempered sigmoids, that is 10H, continually outperform their ReLU counterparts on the 3 datasets that we considered. To explain why such a simple change of activation functions has such a large positive impact on the model's accuracy when training with differential privacy, we looked at the activations of the first layer of our architecture as we did initially when we started exploring this direction. And so here what you can see is, whereas previously we had observed that by training with differential privacy and ReLUs, the norm of the activations had exploded by 2 to 3 times. Now the yellow line on this plot that we've added, which corresponds to training with differential privacy, but this time with a 10H, you can see that this yellow line corresponds almost exactly to the setting where we train with a ReLU without privacy. So what this means is, by switching to bounded activation functions, by switching to tempered sigmoids, and in particular here to a 10H, we are able to bring back the norms of the activations of our model back to a setting which is consistent with learning without privacy, despite the fact that here, for the yellow curve, we are indeed learning with differential privacy. This helps us to learn with privacy because it eliminates the negative effects of clipping and noising large gradients. So by better preparing gradients to the operations performed by DP-SGD, less information is lost. I think that the key takeaway from this work is that rather than first training a non-private model and then later trying to make it private, we should bypass non-private training altogether and directly attempt to design architectures that are more amenable to be trained with privacy. Here we showed that the choice of activations